Modern production facilities operate as dense networks of interconnected IoT devices and high-speed robotic systems working in automated synchronization. These machines are directed by an industrial control system, or ICS. The ICS serves as the digital nervous system, transmitting commands from a central hub to individual robots to coordinate their physical movements. But that connectivity introduces a specific vulnerability. While traditional ransomware targets office files and databases, an attack on an industrial network has a different objective. When malware breaches an ICS, it severs the command signals. This translates digital encryption into physical paralysis, instantly freezing the mechanical production lines. For a major manufacturer, 1 hour of silent machinery can result in hundreds of thousands of dollars in lost yield. Relying on a reactive strategy means accepting those losses as an inevitability. To maintain operational continuity, manufacturers are moving towards a proactive defense, treating cybersecurity as a foundational engineering requirement rather than an IT afterthought. This defense uses a 5-pillar framework to stop cyber threats before they impact physical hardware. The identify phase maps every connected sensor so no shadow devices remain unmonitored. Once identified, Protect secures these nodes with encryption, ensuring sensitive production data cannot be extracted. But protection also requires regular employee training. This is the primary defense against phishing attacks, which remain the most frequent entry point for industrial ransomware. These first 2 layers form a hardened perimeter that can neutralize the automated, high-volume probes used by hackers to find easy targets. By combining complete asset visibility with strictly locked-down access, manufacturers prevent external actors from simply walking through the digital front door of the plant. Because no digital perimeter is ever completely impenetrable, the framework includes interior defenses to catch and isolate any threat that bypasses the outer shield. The detect phase uses AI monitoring to watch for anomalies. If a machine's data output spikes from its normal rhythmic wave, an alert is triggered. The automated respond phase immediately isolates the suspicious node, severing its network link to contain the threat. This quarantine allows the rest of the factory to continue running without skipping a beat. A single infected machine might briefly pause, but the malware is safely prevented from spreading to other critical systems. The final phase is recover. This utilizes redundant mirrored data backups to restore the isolated system to its original clean state. Having these pre-validated backups ready reduces the recovery timeline from several weeks of manual reconfiguration to just a few hours of automated restoration. These fail-safes ensure that a breach results in a manageable, localized pause rather than a total operational failure. Adopting this architecture integrates cybersecurity into the engineering process, making digital protection as fundamental as the physical safety protocols on the floor. Treating network integrity with this level of rigor creates a facility capable of maintaining its production schedule, even while actively defending against an intrusion. This engineering-led approach shields proprietary trade secrets from industrial espionage and prevents the delivery delays that destabilize global supply chains. In an era of total automation, a factory is only as reliable as its network. To keep the physical machines running, the digital foundation must be engineered for resilience.